we talked about the bitness of a microcontroller, right? And we said that the bitness always refers to the data bus. So, for instance, there is a 4-bit microcontroller that you can get from Microchip that has 4 bits on the data line, but it has 24 bits on the address line because it can still address 65K of memory. All right? And that's sort of the whole thing because they stuff I/O and everything else in there. Let's see. Moving along, there is, okay, so you get, in your memory, you have 2 to the n locations, right, that you can do. And, you know, you can do sort of really ugly things, right, with C. We try to not have you do that. One of the things, it's a bit of a religious war. We try to sidestep it, but there's endianness, all right? So there is a big endian versus little endian. All right, and if you haven't turned this, so for a character, for 8 bits, it doesn't matter, right? The 8 bits get stuck in there. They're always from least significant bit to most significant bit. The question is, what byte ordering do you use when you do, for instance, 2 bytes together? So with 2 bytes together, you can do, well, the end is the bigger part, so you have the high and then the low, right, in here, or you can have little endian, which has the low and then the high. Now, what's really interesting about this is, and it's the same is true whether you're using floats, which are 8 bytes put together, right? They'll be in backwards order from one to the other. And for some reason, almost all microcontrollers are one kind, and almost all desktops are the other, which means when you do communication between the two, you've got to swap the bytes every time to do things, which is really annoying. Yeah. Now, within the byte, the order is always consistent. So within each byte, it always goes from least significant bit to most significant bit. It never changes. Right? They don't actually swap the individual bits. It's just the byte order that gets swapped. The bytes are always the same. They always start little and go to big. So in other words, when you put in, so the classic one when you fill memory to figure out what you're doing is you put in hex dead beef. Right? There's a couple of these that sort of spell things you can read. There's dead beef. There's cafe babe. There's a few others that sort of are mnemonics that you can sort of see. What you generally do is you fill the memory with these, run your program, and then look at the memory again to see how high the stack went. Right? Because you generally have the heap starting from the top, the stack coming up from the bottom, and you want to see if you ever crossed. Right? And so you see basically what doesn't read as dead beef or cafe babe. However, if you send this in and then you look at memory, you will often see beef dead when you look at the memory rather than dead beef. You put it in as dead beef and it comes out as beef dead. In other words, the byte order is swapped. The high byte is in the low position. So that would be little endian. Right? And that's sort of very common. It doesn't really matter if you're staying within one or the other. It's only really on communication between 2 systems that you have to start to worry about it, right? Because it's entirely self-consistent, you don't have to worry. Yeah. You know, don't pin me down on it. It's one or the other. I think that this is considered little endian. I'm pretty sure, but I might be wrong. I'd give it 50% chance I'm right. Yeah. Oh, I was just looking at just this one. Oh yeah, you're right. No, you're right that it actually. Yeah, it's. You're right. It actually does that. Yes. It swaps all the bytes in the thing. So yeah, so that's it, because every 2 is a byte. Right? And so it does. It swaps. So this would be one that swaps the order. Right? And so you sort of look at these, and when you look in memory, it sort of becomes obvious which one you're looking at or not. So as I said, you know, inject something you can read into one, and then read it back and see what it looks like in memory. It's really sort of easy to pick off. And as I said, it's not that important. It only becomes important when you start swapping information between two systems that you just need to remember that it exists. All right, and there's a whole bunch of reasons, by the way, on both sides. Like I said, it's a religious war about why you should do it one way or the other down at the transistor level, why it makes sense to do it. But nobody does. Okay. There's ugly code versus clean code. You can do things in C that are really, really nasty, and some people think it's sort of macho to write really ugly code. I do not. I do not belong to the macho ugly code camp. I think, I could say something nasty, but I won't. All right, but you could do things, for instance, like, you can put a line in C that looks like that. All right, so, and it's actually possible, and this is an easy one, right? It's possible to decipher this. If you really want to see ugly code, by the way, there's something called the, just Google ugly C code, and you will see these examples that are just hideous. And they're true, they're very compact, right? But on the other hand, they're not to do. And the thing is, you don't gain anything by it. That's the stupid thing. Right? By writing, there's almost no instances where if you actually look at what the compiler produces on the assembly side, where it actually gains you anything by putting this all in like one squished line as opposed to just separating it out and making it clear with parentheses and everything like that. The assembly is the same. Right? It just, this is indecipherable. Indecipherable. Right? I think that's how you spell that. So you can do all kinds of silly things like that. Don't. You've got plenty of processing power in this class. All right. The last year, it turns out, we had one of the codes set wrong on the clock setting on the thing. We were running it at a tenth of the speed it can normally run at. Nobody noticed. We never noticed. All right. It was, we were running at a tenth. Nobody ever even came close. All right. So and we fixed that, so now they're running 10 times faster. And you're still not going to come close. So that if anyone sort of finds them sort of computationally limited in this class, I'll help you with the algorithms to get to clean that up. All right, but it's not going to happen. All right, very quickly, there are two kind of address space, data space differences in the world. So generally, what we have inside them, we have instructions. All right, these are known as opcodes. All right. We've got data. We've got control registers. We've got memory mapped I/O. Memory mapped I/O, which is how most people do it these days, and things like ports or pins. All right, and so these just sort of look like another area of memory. You write to it, and voltage is changed on a pin that's hooked to the external world. All right, same thing you can just read. For instance, when you read the A to D, you're reading what the voltage level is on that pin, all right, and scaling it for you and doing some other nice things. So there's two kinds of ways to separate out what goes in that. Anybody remember what they are? Give you a hint, one of them is a snobby school on the East Coast. Okay, there you go. See, that always works. So we have the Harvard, and the other one is von Neumann. Anyone know what von Neumann was also famous for, responsible for, other than his work in computer science? No, there's one big one: mutually assured destruction. He was the game theoretician who figured out that if the Russians and the United States figured out that we would always blow each other, the kingdom come, it was stable. He also showed it was only stable with two players, by the way. So as soon as you added China in, it didn't work anymore. But that's a sort of historical aside. All right. So the difference between the Harvard and the von Neumann is, can anybody remember? Right. So in Harvard, you have data in one side, and you have code in the other. They're separate from each other. And in the von Neumann, they say, you know what? Why bother? We're just going to have one big thing of memory. There's going to be data and code. And we're just going to arbitrarily sort of split it in two, and one part's data, one part's code. There are a couple of reasons for doing it one way or the other. This is obviously, in certain ways, cheaper to build. All right? No, you just got one thing. It's easier to build than two. And often a lot of Harvard architectures have, in fact, the two memory sections one basically on top of the other. It has some robustness issues. So a number of years ago, there was a satellite called the Clementine that was sent out to map the moon, and they got a single bit upset event, which means they got hit by gamma ray, caused the program counter to shift. All right, 1 in a billion shot, but lots of cosmic rays bombarding it, and caused the program counter to jump through data, and the thing basically started executing data as code. All right, and so it was just sort of kind of running through there, and managed to sort of dump all of its fuel, firing the rockets randomly before the watchdog timer had time to sort of kick out and reset it. All right, and so that was they lost the satellite for it. It's still spinning somewhere near an asteroid off between the moon and the L4 point. But anyway, it happens. All right, now if you're not doing space qualified stuff, you don't need to worry about it too much because we don't get too much cosmic radiation down here, so we don't have to worry about single bit upset events. But they do happen. There's some other reasons. So for instance, if your data and your code, so for instance, the microchip, the PICs, so the PIC32 is a Harvard architecture, and it has a completely separate data section, a completely separate code, and what that allows them to do is they're actually different widths. So the data section is 32-bit wide, but the code section is actually 24-bit wide. Right? And the reason the code section is 24-bit wide is it allows them to use basically all of their instruction codes go in. It's a RISC architecture, and so they all get executed in essentially one clock cycle. All right? And they all fit in perfectly. All right? So that's one of the ways they do it. So there's a couple of advantages. All right, and just kind of a couple of things to look at. We've got lots of different things about this. Is sort of where the memory map sort of goes. You'll see all these little reserved stuff that they've given us for areas to play with, and those are cool. But here, for instance, is the boot flash. All right, so there's the boot flash. We've got some device configuration registers. They've got this kind of cool thing where they have a virtual section of memory that they can then move anywhere that you can do. Somewhere in here, so special function registers. This is sort of how you set up any peripheral. Goes through those. Program flash. This is the thing you guys are writing in here. Just the idea here is there is a lot, right? There's a lot within this address space that you can get to, and different sections have different things, and they're sometimes interleaved depending on how they do it and where they've added things. So that's there. Anyway, we have on the PICs, I believe we've got 32K of RAM. Right? And at first, if you're used to a desktop machine that has 8 gigs, you're like, oh, good God, that's nothing. Right? But for a microcontroller, this is very generous. All right. So oftentimes, I've had microcontrollers that have 256 bytes of RAM, right? And that's all you've got, right? So you're not loading any large arrays in, right, when you do that, right? And so, 32K is generous. It's not huge. There are a couple that get bigger, but actually, we might have 128K. But in any case, you're looking at Ks, not megs, not gigs of RAM, not on a microcontroller, which is going to teach you, by the way, to be efficient, which is good. On the other hand, it's also going to constrain you a little way. So if you decide that you're going to do, this big giant 16K array, a big 16-bit array that has every value filled, well, you've just used up 65K of RAM, all right? And it's gone, right? You've used up basically all your memory at that point. So you have to be a little careful what you do. Program options. All right, we're just going to go through these really quick. MROM is masked read-only memory. You don't see this much anymore, but this is basically you burn in the program, burn in at factory. Okay, so this is when you're doing, more than a million of these. All right, so basically the first one costs you $100,000. Numbers 2 through 10 million cost you less than a penny a piece. All right, and so the idea is, also the other advantage of it is you can't reprogram it, which at first you say, well, that's not much of an advantage, but it is if you don't want people taking apart your thing and figuring out how it works. All right, it's sort of burned in, you pop the fuses, can't be updated, flashed, redone. Turns out it's not as safe as you think, so they did this, for instance, on the PS3, and the guy at MIT basically sanded off the top and used an electron microscope to basically back out what the code was and hack it. Only a grad student with a lot of time and equipment he can't afford could do this, right? Took him 6 months, but everyone's got to have a hobby. So, all right. The next one, PROM. That's a P. And this is programmable. Read-only memory. And within this, there is the EPROM, which means electrically programmable. And this is a byte at a time. All right, so you can do that. And that came in 2 flavors. Again, most likely you'll never see. But there is the erasable, which had a little window on the chip, a little quartz lens on it. You stick the thing in a little UV light, and it wipes out the memory, and then you can program it again. And the other kind was what was referred to as the one-time programmable, and it was the exact same thing. They just didn't have the window on it. So if you could somehow get UV light in there, it would work. And so when we used to work with these, the way we used to prevent ourselves from accidentally erasing them is you put a little piece of black tape over the top of it. Right? And that was your window, kept it from going. All right. The other one we have is, and this is sort of getting more common, EEPROM. All right. And this is, in addition to being electrically programmable, it's also electrically erasable, which makes it a lot better. And then we get down to what we use today, which is everybody uses Flash. And the difference between Flash is an EEPROM, except that it is, you can only do a block at a time. All right, and so something like, 32K at a time, you can sort of whack it, or 500 bytes to 512 bytes at a time. They'll have a specification depending on how big it is, but you only get to do one block at a time, which means that you have to sort of juggle. You can't just incrementally write in. You have to wait until you have something big enough, and then you whack it. And they have a limited number of cycles, but they're pretty good. If we look at memory, basically the way it goes, we've got SRAM for a static RAM. And static RAM is generally 6 transistors. In order to do it, you do it with flip-flops. Boom, boom. And so you need 6 transistors. And the good news is it's fast, really fast. And if you battery back it, you can easily get 10 years off a little coin cell battery, so it's not going anywhere. Downside is it's expensive. All right, so generally this is where you pay for it. It's expensive, so you don't have a lot of it, but it's really, really fast. And the other kind you have is dynamic RAM, DRAM, which is dynamic RAM. And what dynamic RAM is really a capacitor. Right? A little extra complication around it, but fundamentally, it's a capacitor. And the problem with that means that, like all capacitors, you put a thing on it and it starts to decay. Right? Which means at some point, you transition from a high bit to a low bit through the decay, which means you periodically, before it ever gets to that level, you have to refresh it. Right? So there's a little refresh engine that goes in and constantly sort of lifts everything back up to do that, which means that if you lose power, forget, so there goes your memory, right? Because you're constantly having to refresh it, and if you just don't do anything, it'll all drift to zero relatively quickly. Now, it's got a couple of advantages. So the good advantages are it is cheap. All right, very cheap. It's dense, meaning you can get huge amounts of memory in small packages. On the disadvantage, it's slow, and it's ESD sensitive, which means you have to take certain precautions when installing it to not blow the, if you just mishandle it and you've got some static electricity on you, you will actually blow the little capacitors apart, right? And then they won't work. All right? And then the last one we have that you've all heard of is cache RAM. All right, and cache RAM is simply SRAM that has been optimized for speed. And I mean blindingly fast. All right, so the way you generally have it is your CPU sits in the middle, then you have your cache, and then you have your RAM. And the idea is that if you can, that when you go to RAM, you load as much as you can into cache fast, and then you work out of the cache as much as possible. Lots of people in computer science do work on sort of how to optimize the cache hits to make sure you don't, a cache miss is a big deal because then you've got to go out and reload it. Modern computers tend to operate more than 90% of the time out of the cache, right, which is really fast. And to give you an idea just how fast this is, most of these are stable between 5 and 10 nanoseconds, all right, meaning that you can query it and have the data in 5 nanoseconds. Just to give you a sort of semblance, a ray of light. Does anyone know how far a ray of light travels in 5 nanoseconds? What's that? 5 feet, about that far. So the time it takes light to travel from my left hand to my right, the data is stable and served. All right? That's pretty damn impressive. I mean, it's just, you're down at that level of speed. And by the way, one of the ways they do that is they get the path lengths really short. All right? Because they can't travel faster than the speed of light either. They just make sure that the path length that the signal has to propagate through the thing never has to go more than about 6 inches, right? No matter how sort of tortuous it goes sort of in there, right? Finding things. Anyway, let's see. Other things you find, we've got parallel I/O. All right, so these are what we call ports, which just means that basically there's a pin, a set of pins, and they are attached to the outside world. When you write a 0 to that port, the pin drops to a 0 state. When you write a high voltage, is our hand up there? Yeah. Oh, scratch pad memory is sort of the memory that's RAM, essentially. It's what you get to write to and forget. It's what you're using temporarily, put temporary variables on the cement, as opposed to your program memory, which is what we were looking at before, which is where you store the actual code, which you want to survive between refreshes. All right, let's see. So, general, the ports are programmable, and you can change them from an input to an output. You'll be learning all how to do this. You can often tri-state them. You can make them go to a high impedance state where they sort of just let go. Some of them have pull-ups or pull-downs that you can attach to it internally. There's all kinds of things you can do. Some of them can be fixed direction, where you say, you know what, this one is always an input or always an output. You can't change that one. And generally, they are either of the totem pole variety. All right, so if they are a totem pole, then basically, so this is the output. So this is what we call a totem pole. And what this means is it will pull it high or pull it low on both sides. All right, it will force it to one or the other depending which one of these turns off. And there's often something like that goes on the other side of it to make sure it's always doing one side or the other. And these days these are always FETs, no longer transistors. You get better performance and they go faster. The other kind you'll see is what we call an open collector. Although these days that would be open drain. And the idea is you're missing the top half, right? And so what this means is on the outside of the microcontroller, you need a pull-up resistor to bring it up, right? And what it means is it can force it to ground, but it can't actually raise it. Something outside of the microprocessor has to bring it up. That's really useful if you're using something that has different voltages on. So for instance, we're using a 3.3 volt microcontroller. You might have something that takes 5 volts on the other side of it. Right? If you turn it into an open collector or an open drain, it means that you don't actually have to worry about the fact that your microcontroller can't drive 5 volts. You use a pull-up resistor to pull it up to 5, and you're going to ground it when you want to. So when you let go, it pulls up to 5 volts. When you actively ground it, it drops to 0. And you have to be careful to make sure there's enough current. You don't have too much current flowing in and things like that. All right, and there's all kinds of other things that you can find in microcontrollers. If you haven't taken the microcontroller class, you don't necessarily need to. You'll get better at this, and we can do it. One thing I do might be a little different than what you've seen before, which I'll do. So just so you know, and we have this on the website, right? So here's our Uno, and there is our right there. That's the PIC32. That's the one we're using. And there's a few other little things that are nice here on there. This one is this one right here. That's an FTDI chip. That does the USB to serial conversion for you. It's very nice. It's a nice chip. And there's a lot of other things sort of inside there. We have put these are the schematics for it from Digilant. We put them on. You can look at it. There's all kinds of things we've got on there. We'll learn them as we need them. It's a fairly capable little processor, so I don't need to go through all of them. I'll go through them bit by bit. But one of the things you may not have seen before is the way the development process works. All right, so the development process, development process. So the way this works, normally when you're writing code on a desktop machine, you write the code, you hit compile, you run it. You look at the output, you don't like it, you go debug, et cetera, you're done. All right. This one's a little different in that you write the code on your desktop machine, right? So there you are, writing your code, all right? And so you write it here, then you run it through compiler to generate a file, and then you go through communications bus, in this case the USB, to your target, and then if you're lucky on the target, you have some form of monitor, or in this case, a serial to USB. We go back along the same bridge that lets you know what's going on inside it. All right, and this kind of monitor, there are lots of different ones that you can get if you ever sort of go on. There's things called ICE, in-circuit emulators, where you have this big snorkel thing that comes down from the PC that actually fits on the PCB and looks like a microcontroller. It usually clamps onto the pins of the microcontroller and takes over everything. In this case, there's on the microchip ones, what they do is they take over 2 pins, and if you actually put the programmer on, you can halt the processor, look at any register, look at memory, do anything like that. In general, we won't be using those in this class simply because you have the ability to sort of flounder the bootloader that we put on there for you. And if you have some really obscure thing going on, we'll bring it out and we'll figure it out. All right, but that's usually we don't need it. All right, but those are available.